Okay, so we're going to look at integration by parts on this video. It's section 8.1 as we get deeper into Calculus BC. Very many integrals that we've done in the past have been through either an obvious antiderivative, applying some algebra, and then being able to use antiderivatives, or even using u substitutions. But today we're going to reverse the product rule. So let's just start off. I've already written this up here on the notes. Let's say that we have two functions multiplied together, and we'd like to take the derivative of them. dx of f times g. We know that one way we could write that is f prime g plus fg prime. Well, let's just say we wanted to integrate this equation. We'd integrate on the left, we'd integrate on the right. And right now this might look a little strange, but let's go ahead and make a couple of substitutions. Let's let u equal f. Both of these functions are functions of x. So I could say very quickly that here we'd have du. Over here we could say this would be f prime, whatever derivative we're going to take the derivative of f is. And then we could say this would be dx, because f really is a function of x. Similarly, we could say v is equal to g, and then dv would, of course, be g prime dx. Now, what I'd like to point out real quickly is we could take a look at g prime dx right here and say, oh my, look at this. We've got g prime dx likewise over here. I can take a look at f prime dx and very quickly notice that I have an f prime dx in this other integral. So of course what we could do immediately is just realize that we're going to effectively just take our derivatives here that we just did up on the top, and we can make some substitutions. We could say this integral f prime of dx is really a du. And what about g? G, of course, from up on top is just going to be v. Likewise, we can say that f was substituted in for a u. G prime dx could be more simply written as dv. And then very quickly what we can point out on this left-hand side, we know that if we wouldn't even have made that simplification at first, we'd say, well, what's the integral of the derivative of f times g? Well, you could say, well, isn't that just f times g itself? But f is u, and g, of course, is v. So we could be left very simply with a uv. You might wonder if we'd want to put a constant out. We could delay that for a moment. Well, suffice it to say, what I'm going to do real quickly is bring this over to the left, this integral of v du. And right now we have something quite remarkable. I'm going to recopy this up here. This is known as integration by parts. This right-hand side I'm now going to move over to the left. Let's just say that we have an integral of u dv. According to what we've just proven here, if we look on this other side, that would be uv minus the integral of v du. Now, it just so happens that the substitution rule, the u substitution rule, sometimes is going to fail us. We've seen integrals where that could happen. This is going to be an alternate way to approach integrals. And we're going to say, what if we're starting off with some integral where it's in the form of u dv? If we could make an appropriate substitution for u and dv, we could get this formula on the right and rewrite that integral in an altered form that might be easier to finish off. But this is very important for our choice of what u is. The choice for u, what we do very often is use an acronym. This works 90-some% of the time, and we use this late acronym here. L stands for logarithms. Okay, so we've got logarithms for L. A stands for algebraic expressions. T stands for trig or inverse trig expressions. and E would stand for exponential expressions. What we're really getting at is we could let U equal, first, anything logarithmic. If we don't have anything logarithmic, then jump to algebraic expressions. If we don't have algebraic expressions, let U equal a trigonometric expression. And last but not least, let U equal something exponential. I think what really has to happen is we need to see this in action. Take a look at example 1. Stating the obvious, we don't know an obvious antiderivative for x sine of x dx. Similarly, if we just tried to do a basic u substitution, no matter what we choose for our u substitution, it wouldn't really be helpful. But we do see a product of two functions in here, and we might wonder if we could somehow reverse that product rule. Well, let's see if we could real quickly jump on in. What this is really saying, guys, if you were to look up here, if we have this integral of u dv, and that's honestly what we're saying is, could we think of this integral right here as the form of u dv, then we might be able to say, well, what would u be? Well, u, according to the acronym of LATE, we'd say, do we have any logarithms in the integrand? Do we see a natural log or perhaps a base 10 log? The answer is no. Do we have anything algebraic? Something with x to a power, more than likely. We do. We could let u equal x. Well, what has not been chosen in the integrand, the non-algebraic part, would be the sine of x dx. What we're going to do then, of course, is have a dv. dv would be sine of x dx. Well, once we have a choice for what u would equal, and then by the process of elimination also knowing what dv would equal, now we could go ahead and take a derivative for u. We'd have du would equal, well, the derivative of x would just be dx, 1 dx, if you would. Now we're going to take an antiderivative. We could say, well, what's the antiderivative or an integral of 1 dv? Well, that would just be a v. What's the antiderivative of sine? Well, hopefully we'd agree it would be negative cosine of x. And we could very quickly double check that that's right by taking our derivative on both sides. Well, you might wonder, well, has this helped us? What you want to do is have this form memorized, the uv minus the integral of v du. What was our u? Well, it's x. How about our v? Well, it's negative cosine of x minus the integral of, now what's our v? We could say, well, that's negative cosine of x. What's our du? Well, plain and simply, it's just dx. Look at this new form. Yes, it has a non-integral part to start off with. That's your uv. And we do have an integral remaining, but look, the minus the negative turns into plus a positive, and it's a simpler integral right now. If all I had was just this cosine of x dx, well, we could work that out. The antiderivative of cosine is sine. Now we're going to throw in our constant. We'll put in our plus c, and this is it. This is known as integration by parts. And hopefully that's helpful in seeing this new process. Again, when do we use integration by parts? Well, you should always proceed. Let's look at number 2. Say, do you know an antiderivative for the natural log of x? Well, we don't. Could a u substitution help? Well, you could try it, most certainly, but it won't help us out here. So what we're going to do instead is jump over to that LATE acronym. And again, we're assuming that this is an integral of the form u dv. We could say, well, what would we let u equal? Do we have any logarithms? We do. U would equal the natural log of x. Well, what haven't we represented with our u? Well, the only thing that's remaining in the integral is dx, and that's what our dv would have to be. Let's take derivatives. du would be 1 over x dx. Antiderivative here would get v is equal to, plain and simply, just an x. Well, now what? Well, we have uv minus the integral of v du, and u times v, well, we'd get natural log of x times an x minus the integral of x times, well, what's our du? It's 1 over x dx. Now I'm going to put my x out in front of natural log of x. I think that might help out a little bit. This x and the 1 over x are going to just leave us with a 1 dx here. And if I took the antiderivative of just 1 dx, I'll have my minus out in front. Here's my x. Don't forget a constant. So wow, look at that. We've found a way to evaluate this integral. Let's continue on. Sometimes things don't work out quite as simply as we'd like. Let's take a look at number 3. You might wonder what we might try first. Obviously, it looks like it's an integration by parts problem. It looks like we have a product. First choice is obviously to go through previous methods. That being said, do I have anything logarithmic? No. Do I have something algebraic? Yes. I've got x squared. So I'm going to let u equal x squared. What would dv equal? Well, dv would equal e to the x dx. Here I'd have du would be 2x dx. And then I'd have v is equal to just e to the x. Look at that. Well, you could see we'd have uv minus the integral of v du. And if we work this out, uv, we'd have x squared times e to the x minus this integral of e to the x. Now we have 2x dx. And at first glance, it looks like we're in trouble. You can say, well, yes, I've done my integration by parts. And yes, things have gotten perhaps a little bit nicer. You can even pull a 2 out. You can pull the x out in front here. But very quickly, kids will correctly point out, now wait just a minute. This antiderivative of x e to the x, I don't know. Well, guys, there might be times, and here is one of them, where you're going to have to use integration by parts twice. So once again, let's see, just focusing right now, please understand, our focus is just on this integrand. We could say, well, let's see here. What would we let u equal? Well, something algebraic, of course. dv, we could say, is e to the x dx. We'd have du would just be dx. Antiderivative here would get v equals e to the x. And now what? Well, we have x squared e to the x minus 2. I'm going to put some big brackets right here and put our new uv minus the integral of v du. So we just have to work that out real quickly. We still have that minus 2 out in front. We can distribute that in a moment. U times v now, we'd have x e to the x. This integral is going to look nicer now. We'll just have e to the x. Du has finally just simplified greatly to just a dx. So hopefully you can see this is going to help us out considerably. You want to distribute that minus 2 in right at this very moment. You can. Negative 2 times a negative would turn into a plus 2. You could even distribute after you work out that integral. It's completely up to you. But my goodness, just finishing this problem up, the antiderivative of e to the x is e to the x. Don't forget your constant of plus c. Okay, so let's move on to number 4. And this one has a little bit of a surprise to it. For number 4, usually kids look at this and they'll say, well, it looks like a run-of-the-mill integration by parts. It doesn't look any more complicated than our last problem. Let's use our LATE acronym and say, what could we let u equal? Well, no logs, nothing algebraic, but we do have some trig. We can let u equal sine of x. dv, you might guess, would be e to the x dx. And then you'd say du equals cosine of x dx. Take an antiderivative here, you get v